Good morning to all. Welcome for the today's session. Signaling over additive white Gaussian noise channels, that is geometric representation of signals. So in the previous video, we have discussed about the block diagram of the signal whenever we are transmitting a signal over the additive white Gaussian noise channel, right? Today, before we really get into the main topic, that is geometric representation of signals, we need to have little bit mathematics background. So we have to create a framework of mathematics to analyze this chapter in a better way. So first we need to understand the vector space. For this, to make you understand the vectors, let us consider the 2D vector space. Okay, and it consists of x vector, x axis as well as the y axis. Let us consider the vectors p as well as q. Okay, if we add this vector, okay, we will get the resultant vector such a way it is marked in green color and it is labeled as R. And also, suppose if you multiply this q vector with minus 1, okay, we will get the vector that is G, that will be in the fourth quadrant. Okay, so the resultant vector will be R, as well as if you multiply the vector q with minus 1, we got it as G vector. So all four vectors are confined to a 2D space, right? Now let us define the vector space. What is vector space? That is nothing but the space consisting of vectors together with the associative and commutative operation of addition of vectors and the associative and distributive multiplication of vectors by scalars. So in order to get into this geometric representation of signals, we wanted to know what is vector space and how we are going to represent the vectors in the two-dimensional spaces. Okay, then followed by this, let us consider the basis function. So for this basis function, again we consider the two-dimensional vector. Here we represented the vector q, right? And we will consider the two unit vectors. Okay, and we can label it as j as well as I. Okay, so these two vectors are unit vector and it is orthogonal to each other and also orthonormal, that is I and j are independent of each other. Okay, so if we multiply I and j, we will get I and j is equal to I multiplication of j should be 0. Therefore, we will call it as this is no independency. Okay, that means this is our I and j are independent of each other. And if you multiply I cross I, that means we will say it once again. That means whenever you multiply I cross j, I product of ij, that is 0. Okay, that it shows that I vector and the j vector are independent of each other. The same way, if you multiply I cross I, that is equal to 1. It shows that this both vectors are orthonormal. Okay, so because of these properties, we can define any vector in vector space. And also one more thing, if you multiply this q vector, with 4i plus 4j, okay, that means see 4i plus 4j, and also you can use the properties that I cross j and I cross I. Okay, now let us trying to make you to understand that unit vectors in terms of coordinates. So let us write the coordinates. That means two basis function phi I comma phi j, that is equal to 0 when I is not equal to j. That means we will call that is orthogonality. Okay, whenever the phi j comma phi I is equal to 1. That means the condition I is equal to j. This is called as orthonormality. This is called as orthonormality. So, in an n-dimensional vector space, any vector can be conveniently defined as the linear combination of basis function. So, according to this condition in two-dimensional space, we can write the vector S in terms of basis function, that is equal to x is equal to x1 into phi 1 plus x2 into phi 2 up to xn into pi n, and it can be abbreviated as summation I is equal to 1 to n xj into phi j. Okay. Now, let us discuss about the relation between signals and vectors. So, how we are going to represent the relation between vectors and signals? Okay. So, there are 6 parameters are very similar to this. Let us discuss one by one. The first is projection of two vectors can be seen as inner product of two vectors. For example, let us consider the two vectors named as g and x. Then that is given as the multiply, that is inner product of g into x into cos theta. Okay, and if you come to the signal side, that is projection of two signals, it can be also represented as inner product of two signals, but we can write integral 0 to t g of t into x of t into dt. Okay, and coming to the orthogonal properties, if there is a two vector, if we say the two vectors are orthogonal, then the mathematical expression is g comma x is equal to 0. And if two signals are orthogonal, then we can say that integral 0 to t g of t into x of t into dt is equal to 0. If we coming to the length, for length of the vector, how we can explain? That is modulus of, it is x comma x, so that double modulus of x the whole square. And if you coming to the strength of the signal, actually, okay, if we coming to the strength of the signal, it can be given by ei is equal to integral 0 to t g of t into x of t into dt. So followed by that, again we will consider basis function of n-dimensional vector space for the vectors as well as basis function of n-dimensional for the signal space. If it is a vector space, just we can recall that what we have analyzed just now. Phi I comma phi j is equal to 0 when I is not equal to j. That is called orthogonality property. And whenever phi I comma phi j is equal to 1, whenever the condition I is equal to j, vector I is equal to vector j, we will call it as orthonormality. So coming to the signal space, so integral phi I into phi j of t into dt. That means when 0 when I is not equal to j, 1 when I is equal to j. And coming to the vector, when we are going to define a vector in n-dimensional vector space, how we can define it? X is equal to summation j is equal to 1 to n xj into phi j. Coming to the signal, we are going to define the signal in an n-dimensional space. X of t is equal to summation j is equal to 1 to n xj into phi j of t. So this is the way there is a relationship whenever we are going to represent the vectors in n-dimensional space as well as signals in the n-dimensional space. And the last, suppose we are considering a unit vector or a basis vector, how we can determine the vector, determine from the vector space. For that we can use phi is equal to v divided by double modulus of v. But suppose if you want to determine the basis function from the signal, then we can use the formula phi of t is equal to x of t divided by root t. X of t is nothing but the signal and E is nothing but the energy of the signal. So these all are the more correlation between the vectors as well as the signals whenever we are representing in the space, signal space as well as in the vector space. Next we'll consider about So hope we understood actually how to represent the vectors in the two-dimensional space and what are the relationship between the vectors and the signals. Hope everyone understood this. Thank you for watching and thank you.